everybody. So this will be a talk about sketching complexity of graph cuts, and this is joint work with Robbie Krofgamer and David Woodruff, who you have just seen. Okay, so let me start. So before, this is about a particular result, about a particular construction, but just to kind of place it in the context, where the question comes from. I just want to spend kind of very quick slides from kind of slightly bigger picture of what's happening. And what's happening is, in general, we may be curious about the questions of graph compression, which means that we have a big graph. We want to construct a smaller graph such that this smaller graph somehow looks like the big graph, right? And I guess here by picture I'm kind of suggesting actually, smaller number of edges, smaller number of vertices. We will talk only about smaller number of edges here, but in general, as a general principle, you can think about smaller graphs, and then you begin to, of course, the question is why do we want to do it? Why do we care about smaller graphs? Of course, there are maybe many applications. One that surely runs through as a theme in this entire workshop is faster algorithms. Once you construct smaller graphs, algorithms become faster. Also, in other applications, you may want smaller graphs because you want to use less storage to just represent this graph. Sometimes, some other applications, if your graph is much smaller, that it's easier to visualize or to play with if you want to kind of discover some properties like a social graph or something like that. Okay, and of course, I put some squiggly here saying that roughly approximates, and of course, the main question is what do we mean exactly by these approximates? And in general, you think about this as preserving some kind of structure. So, for example, one particular structure that we will be talking here and runs as a theme in our talks is to preserve the structure of the cuts. So what I want is that I'll construct another graph on the same set of vertices so that the cut values are approximated, are equal or approximately usually, just to obtain smaller graphs we usually need approximation. But in general, you can imagine other properties like distances, flows, electrical conductance, and so forth. Okay, so this is just placing in a bigger context. I'll focus here on cuts. Okay. All right. So for cuts, from the definition, I'm sure all of you know the definition, but just to put it on the same page. So we have a graph G with n nodes, m edges. We want to construct another graph, we call it H, so that for any set S of vertices, the cut in graph G is roughly approximated by the cut in graph H on the same set, and approximated, we'll think about 1 plus epsilon approximation. Okay, standard definition of cut sparsifiers. Okay, so, a very classic result is Bencher-Karger from '96, which says that we can construct a graph H, which has the number of edges is only n divided by epsilon squared times a log factor. Okay, so we can start from potentially a quadratic size graph to something which is n divided by epsilon squared times log n. And, the general approach is to sample edges in the graph. The sampling has to be non-uniform, so we cannot just take all the edges and just uniformly sample them. As this counterexample, is a classic counterexample why we cannot do this. And of course, the question is how exactly do we do sampling here? And in some sense, this is the main question in this line of work. And there are many ways to sample edges according to different notions of connectivity in the graph. And all of these results which sample edges will, in general, as I mentioned, we can use this to speed up cut problems. And in general, all sparsifiers will obtain size which is n divided by epsilon squared times some polylog. So some of them will obtain log, some of them will obtain log squared maybe. But in general, this is the type of results that you obtain via this kind of approaches. Of course, there is the question of can we do better? And the answer is yes. There's a beautiful paper, Batson, Spielmer, Stavar, who proved that you can get rid of the polylog factors. Okay, so you can obtain the number of edges only n divided by epsilon squared. And it is actually a deterministic algorithm. Okay, so okay, so this is, okay, so what's next, kind of? So there is a dependence on epsilon. Okay, so what we have is we have a dependence on epsilon which is quadratic. So it is n divided by epsilon squared, and it is natural to ask, is this dependence, quadratic dependence on 1 over epsilon, necessary? In general, factor of 1 over epsilon, if you think of epsilons like, 1% can be more expensive than a log factor. But, think about kind of theoretically, can we beat this 1 over epsilon squared factor? And in general, it seems hard to avoid 1 over epsilon squared. So there are some lower bounds saying, but at least for spectral sparsification, which is a generalization of the cut sparsification, so for a harder problem, at least, you do need n divided by epsilon squared. So this is optimal. Okay? Still, kind of, first of all, okay, this is for a harder problem, and, maybe for our cut sparsifier, we can actually get n divided by epsilon. It is worthwhile to at least verify this, to see. And also, algorithmically, and I'll get back to this issue, but algorithmically, if you look at the lower bound, from the kind of, as an algorithmist, I'm not particularly satisfied by these lower bounds, because these lower bounds say that, well, if you have a complete graph and you want to construct a small sparsifier, you cannot beat the n divided by epsilon squared size. But if it is for a complete graph, I know exactly what are the cut values, right? It is not a satisfying lower bound, right? It is not something that, I know exactly what are the cut values, right? So, at least maybe for applications, we can, change the notion a little bit, or somehow, go around that. Okay, so let me, just state the results. So again, for the cut sparsifier problem. So first of all, we prove a lower bound that says that, yes, indeed, for cut sparsifiers, n divided by epsilon squared size is necessary. Okay, so, just answering the question, yes, it is, even for this, in some sense, simpler problem, n divided by epsilon squared is necessary. On the upper bound side, we show that actually, if you change the notion, well, what exactly we mean by cut sparsifier, we can obtain a dependence which is just n1 by epsilon. So in particular, we'll give a construction that gives a size 1 divided by epsilon times polylog for a relaxed notion. What does the relaxed notion mean? There are two relaxations. So one relaxation is that instead of a graph H, where we compute the cuts in the usual value, we will construct a sketch, which you can think about as a data structure. It doesn't look like a graph, but something else. And it works the following way. You give a set S to it. You tell it a set S. It outputs, outputs the cut of S, right? And this value cut S is 1 plus epsilon approximation of the original cut in the graph G. Okay, and this sketch has this size, okay, n divided by epsilon, polylog. So this is relaxation 1. Relaxation 2 is that for every cut S, so think about this as a data structure which has high probability of success. So for each set S, it will answer will have this guarantee with high probability, instead of all cuts at the same time, right? So for a graph, you don't think about this kind of randomized guarantee. So, for those who know kind of the difference of for each versus for all, let's say in compressed sensing, this is exactly this difference. This is a kind of for each guarantee. Okay. Are there questions about statements? Yes.
Trees work for that or not?
Do Montgomery Who trees work for, what is that?
I thought there was a tree for which you get exact cuts, right?
All the mean cuts between ST.
Right.
This is for all cuts. I give a set S, and I want cut value of the set S. Other questions? Okay. So let me give kind of, run through motivating example. In particular, say, why relaxation goes around with, let's say, complete graph. So, let's look at complete graph kind of, and see why, why kind of in standard notion we kind of need 1 over epsilon squared, as opposed to why in this sketch we can get around with 1 over epsilon squared bound. Okay, so suppose that we sample each edge of probability something like S divided by N, which means that that degree of each node in particular will be something like S plus minus root S. This is just standard deviation which you can, just to write it in, kind of what is a multiplicative approximation. It is multiplicative approximation is 1 plus minus 1 over root s, right? So if we consider vertex cuts, right, then in some sense we need to set s to be roughly 1 over epsilon squared to guarantee a 1 plus epsilon approximation. Even with constant probability for a particular vertex cut, right? Of course, you can ask the question, maybe there is another way to kind of do the sampling, and the answer is that no, in general, you cannot really do other types of sampling. This is the best you can do if you really want to construct a graph. On the other hand, again, kind of coming to this intuition, okay, if it is a complete graph, then, I can just, let's say, store the degrees of, the degrees of all nodes, or, for complete graph, I know exactly what are the cut values. I don't really need to store anything. And, so I can store, for example, if you imagine this as being g and half, for example, right, then, storing the degrees makes sense. But, of course, you can ask, like, okay, there are other cuts, and for other cuts, you may need to store need to store more numbers. But if you are to consider, let's say, very big cuts, kind of, which cut the graph roughly in half, then the number of edges there is roughly n squared, and if we sample from a much larger pool, so we have a much better approximation. So for those cuts, we shouldn't care about this. There is a question?
About the case, the weight of each edge is 1, right?
In the original graph, yes.
Okay.
The lower bounds hold even if the resulting graph is weighted. So.
But the procedure that you're going to show will hold also for weighted graphs?
Yes, absolutely, yeah.
Okay.
Yeah, the algorithm, our construction, the upper bound, will work for weighted graphs as well. Okay, you will need the number of, the representation will depend on log of a max on the aspect ratio, kind of. If you have edges which are very big, you might need to store those values at least. So, but okay. So this is the example. Okay. So these were the statement results, the intuition. Now I'll actually give you construction. Any questions so far? No. Okay. So the upper bound. So I'll give you construction. The description of the construction is composed of 3 parts. I will describe the sketch, basically how do we construct. The sketch will actually look like a sample of a graph, more or less. To be a sample of a graph, it will still kind of sample edges, but in a slightly different way, plus a little bit more information. I'll show that the sketch size is what we claim to be. In particular, this polylog is log squared. And then I'll show how to use the sketch to estimate the cut values and essentially give an intuition why this works. And I'll focus on unweighted graphs. But the extension is simple, especially that we have a sketch. Okay, so this sketch construction, so it will fit on this slide. And let's go slowly through it. So there are 3 steps in the construction. So step number 1 is we will guess a coarse cut value v. So what it does mean coarse? Coarse means up to approximation factor 2. Okay. And suppose we know the cut value up to approximation factor 2, right? Let's this approximation be v. So let's fix this v and say that our cut that we want to estimate, we don't know it at the moment, but what we want to estimate will be roughly value v. What we do is we downsample all the edges uniformly with probability 1 over epsilon squared times 1 over v. Basically, this means that all the cuts of value roughly v will become a value roughly 1 over epsilon squared. Okay? And in general, what does it mean to guess? You'll prepare for all possible values of v, and there is only log n of these values. Question?
So the probability is independent of the weight of the edge?
The graph is unweighted.
You said the upper bound applies for weighted.
It does apply for weighted. I'm describing here just the unweighted case. If you, extension to the weighted case is relatively simple, actually. We can prepare, build a sparsifier for each potential kind of group of weights, for example. Or do some important sampling. This construction is for unweighted, but the modifications for the weighted case are minor. Okay? Okay, so now, this is step number 1. Step number 2 is, what we do is we decompose the graph along sparse cuts. What is a sparse cut? Basically, in any connected component, so this is a iterative procedure, in any connected component C, if there exists a subset P such of, let's say, at most half the size, such that the cut value of P in the sample graph is at most something like 1 over epsilon times P, right? So this is a, sparse cut of sparsity 1 over epsilon. Then we store these cut edges, basically, along the sparse cut. We store these edges separately. We delete them from the graph and repeat on the remaining graph. Okay? Part 3, in the remaining graph, so after we have performed this, right, we have a bunch of connected components which do not have any sparse cuts in this definition. So what we remember is essentially the connectivity structure, right? What are the connected components? The degrees of each node. And for each node, we sample 1 over epsilon edges, outgoing edges. Okay, note that we can do the sample just because we know that the degree of each non-isolated vertex has to be at least 1 over epsilon, otherwise it is in a sparse cut. And just to make sure what this sketch actually stores, it stores these cross-cut edges while we are performing this procedure, and basically this information, meaning the connectivity after we remove sparse cuts, the degrees of all nodes, and a sample of 1 over epsilon edges out of each node. Is this sketch clear? Right, so basically step number 1 says let's kind of normalize the graph so that the cut value is roughly around 1 over epsilon squared. Then we decompose along sparse cuts and remember these edges crossing the sparse cuts. In step number 3, we essentially just remember the connectivity structure, the degrees, and a sample of 1 over epsilon edges from each node. Okay, so let me even go for talk about sketch size. So basically, just summarizing what we store the edges across sparse cuts. We store node degrees and connectivity structure, and a sample of 1 over epsilon edges out of each node. Okay, so we want to show that this is bounded, that this is n divided by epsilon times polylog, and this is obviously takes essentially order n space, order n words. Sampling 1 over epsilon edges takes n divided by epsilon space. So what remains is this first part. And for this first part, we can prove, it's a relatively simple claim, that that edges across sparse cuts are only n divided by epsilon times log n. There is only that many edges across the sparse cuts. Okay, and we'll prove this claim now. So. This one? Okay.
So in step 2, do you recursively do it? Because when you cut the graph, then it could be that pieces now have to be cut again.
Recursively, precisely.
You keep doing it until the pieces no longer have any sparse cuts, right?
Precisely. Yes, thank you.
Okay.
Yes. So this is recursive. Yes, thank you for the question. It's a good point. Yeah, and I mean, once we cut the graph, there could be new sparse cuts that start appearing once we continue this process. Okay, so it is in some sense, very iterative procedure. Any other questions about the construction? That's pretty important, right, for the rest of the talk. Okay. Okay, so let me prove this claim that the number of edges across the sparse cut is only n by epsilon times log n. So first, once we found a sparse cut, right, we store at most, the number of vertices on one side times 1 over epsilon edges. This is just by definition of the sparsity, right? Now, what we'll do, we'll use a charging argument, a simple charging argument, and we'll say we'll charge these edges to the nodes in this set P. Okay, so once a node participates in such a sparse cut, it will get assigned 1/epsilon edges. Okay, but what happens is that once a node is charged, this means that it participates in a sparse cut. This means that the size of its connected component decreased by a factor at least 2. Perhaps much more, but at least by a factor 2, which means that a node in particular can be charged only log n times. And that's it. So overall space is essentially, just summing up everything. It's n by epsilon times log n, and this log n is just for the guessing part. So guessing the value. Make sense? Questions?
Is that 1/epsilon edges after you remove the sparse cut, or in the original graph?
So can you repeat the question?
The sample of 1/epsilon edges out of each node.
This one.
Right. Is it after you remove the sparse cuts?
Precisely. Yeah. Yeah. So again, you do uniform sampling at the beginning. Then you remove along the sparse cuts iteratively until there is no more sparse cuts. Once you are done that, you store these and you store a sample of 1/epsilon edges out of each node.
Okay. But you don't combine it into a single graph. You keep these as separate data structures.
You can think about this as a graph. Of course, the edges across the sparse cuts is a graph. The sample is a graph, but we will treat them differently, those edges here. We know which edge came from which part, and we'll treat them differently. So it will be clear from the estimation procedure how and what. Okay, so it remains to describe the estimation. Okay, so we have done all this sampling, we remember all this information. Now we're given a set S, we need to estimate the cut value of S. Okay, so again, just by assumption, by guessing assumption, V is a factor 2 guess of the cut value of S. So the estimate will be basically some normalization term times the sum of two terms. One term is the number of sparse cut edges in the participating in the cut S, basically crossing from S to not S. Okay. And the other term will have, itself a few terms. Basically, for each dense component, what it will do, it will sum the degrees inside S intersection C. There will be a picture on the next slide. I'm just, describing roughly how it looks like. So, the picture will have a lot of components. So, I first want to give the simple, a simple description. So for each dense component, what happens is that normally, if your sketch is actually a graph, what you do is you have a cut, you'll just count the number of edges crossing the cut. What we are saying here is that there is a different estimate which will give you this. Namely, you count the sum of the degrees inside the one side of the set, and then you subtract the estimate of the number of edges inside this set. Okay, so note that this, in some sense, is a deterministic quantity, right? There is, model of the original sampling, uniform sampling, but some of the degrees we stored precisely, whereas this is the part that uses these sampled edges, the 1/epsilon sample out of each node. Okay, so let me. This normalization is just epsilon squared times V. Just to get basically Horowitz-Thompson estimator. Okay, so estimation illustration, this is just, writing in formula what I said on the previous slide. There will be a picture here. The color coding will correspond to the picture. Okay, so this is, just this introduce a little bit of notation. So basically, this is our graph after we have removed the sparse edges. Okay, so basically each of these blue blobs is the dense component, which doesn't have any sparse cuts inside. This is our set S, right? It cuts a few of them, let's say. So we denote by C one of these blue components, these dense components. SC is essentially intersection of the C with set S. So basically this is this part. Okay. So basically, this now introduces all the notation. So for each dense component, we will sum up the degrees of nodes inside this part, minus the estimate. This is just a normalization term. Estimate of the number of edges, internal edges here. Okay, this is this estimate, which is computed from the edges that are sampled. Okay, so basically just vectorially kind of will be a number of edges that go everywhere. The edges that the green edges are the edges that participate in this term. Okay, the black edges don't participate in this sum, and the red edges participate in this sum. Okay, so all the remember that the structure remembers kind of the edges across as well as a sample of number of edges from each node. Okay. Does the estimation procedure make sense? No? Okay.
I thought you store all the edges in the sparse cut.
Sorry?
I thought you store all the edges in the sparse cut.
You store all the edges in the sparse cut, but not all the edges in the sparse cut participate in your estimate. Okay? So there are two types of edges, right, that are stored. The edges that are across the sparse cut and the edges that are sampled from each node. Okay? So the edges that are stored across sparse cuts will participate in this green term. They may or may not participate. And the sampled edges participate in this estimate, in this red estimate. Okay, in some sense, think about this that normally, if we take a graph and we sample a number of edges, or somehow remember a number of edges from it, the normal estimate, right? You can think about a cut sparsifier in the usual sense, where we have just a graph as it is an estimation procedure given a graph, and it says that I have a set S. I basically draw this line, and I count the number of edges that crossed that line. Okay, so this is one way to do estimate. There is another way to do estimate, namely count the number of edges inside count the degrees, sum up the degrees of the nodes inside S minus the number of edges which are internal here. Right, this is another estimate of the number of edges that go across. Okay, and basically we use in some sense two estimates, and one is the first type of estimate is used for the cross-cut edges, for the edges that cross the sparse cuts, and the second type of estimate is used for edges inside dense components. So at least it should be obvious that the expectation of this gives us the right cut value. I need to argue to you that why doing this is better, and namely we will show that the variance of this is better than the variance of the normal estimate. But at least in the when you construct an estimator, kind of probabilistic estimator for some value, first thing you should check that it is not biased, right, or the bias is very small. That the expectation of your output is equal to the right value.
This is supposed to have better variance because inside the component you're denser than across the cut S?
In a sense, yeah. Yes. At least this is a good question to ask. I will explain in the next couple of slides why the variance is better. But this is the right question. Are there any other questions so far? Okay. Okay, so let me basically correctness composed of 3 steps. 2 of them will be simple. The third one will be the heart of the matter. So we need to prove that each of the 3 steps will preserve the cut value up to approximation 1 plus epsilon. So there are, the first step was to downsample down to 1 over epsilon cut value. Right? So we said we guessed that the value is something like that. We sample down the edges uniformly, so that the cut value from V becomes 1 over epsilon squared. And just the kind of usual sampling, kind of uniform sampling says that if we sample down to something like 1 over epsilon squared items, then the multiplicative approximation is 1 plus epsilon. Okay, so the first step says that for our cut value, the approximation that we introduced is only 1 plus epsilon. Okay, so step 2, I mean, basically this the green part, right? What is its error? Well, since we store the edges across the sparse cuts, exactly, we know exactly what they are. There is no more sampling. There is no more additional approximation introduced. So the only additional thing that we need to verify is that the edges inside computing this red sum, right, of edges inside the dense component introduces at most a 1 plus epsilon approximation. Okay, so this will be, and as already pointed out, that the idea here is to show that the estimate of the number of edges inside S has less variance than if we were to use the normal estimator, namely the number of edges across the cut using this sample. Okay, so, and here, here is the intuition, basically. The intuition is the following. So, the number of, so let's concentrate on the dense component only, right? Just forget about everything else. Let's focus on this third part. We have a dense component. We need to show that that dense component has a multiplicative 1 plus epsilon approximation. So, the number of crosscut edges, basically, so this is a dense component, this is the set S, this is our set P, so this is the inside. So the number of edges that cross the cut can be of value roughly 1 over epsilon squared. Right? It cannot be much more, first of all, just because of the first step where we normalize the cut value to 1 over epsilon squared. So it cannot be much more. Now, the problem, why doesn't normal estimator work? Why sampling 1 over epsilon edges from each node does not work? It is because we can have one node that has this 1 over epsilon degree, 1 over epsilon squared degree, and all these, if we just sample 1 over epsilon edges out of this node, we will just not have a good variance for this estimator. Okay, so the problem is, really kind of in the extreme cases, we have one node, big degree, everything goes on the side, and that will have bad variance, yes?
So, I'm a little confused why this effect only happens for one node, but not for two nodes. Like, does it just taper off so quickly?
I'm just showing kind of a bad example in some sense.
One node isn't the worst case, but it doesn't mean that.
Yes. But your sketch seems to handle the one node case as a very special case. Because it's recording the degrees.
Sure. Yeah, I'm just. The estimator, does not think about this as one node or many nodes, right?
Think of it as doing the same thing for two nodes. It's like storing the out degree for the total out degree of a set of two nodes. It only differs by the one. It's like the degree of one plus the degree of the other minus one. So he's really not. So it's almost the same as having for all small sets, storing the set number of out edges for those sets.
Yeah, that's a great explanation. Yeah. So we cannot. One idea would be to say that the set is so small that the number of edges inside is so small that it is insignificant. So this is not the case, but this number can be estimated well from our sample of 1 over epsilon edges per node. Okay, and basically what we show that there is no such issue for internal edges. Why? First, we will show that the set S is small. It is something like 1 over epsilon, which means that each node cannot have a big internal degree, right? So basically, to have a large number of edges, this means that they have to be supported by many nodes. But if you have many nodes, then you have many more samples, right? Each node comes with some edges and a budget of samples. So the more samples we take, the better the variance becomes. Okay, so let me show at least the part number one that this set is small. In some sense, somewhere we need to use that we use sparse cuts, not just for the size, but also for the estimator, right? And this is where it comes. My set SE is I want to say that, at least for dense component, if we look at the set, it is small. Why? It is, so first, there are two statements. One is that the cut value has to be at least 1 over epsilon times SC, because this was not a sparse cut. On the other hand, the cut value of SC is at most something like 2 divided by epsilon squared, just because we guess the right cut value up to a factor 2. Putting this together gives us an upper bound on the size of the set. Okay. That's really it. Okay, so now, I'm not gonna do the computation, but this is really the intuition that I explained. That now if you take this sum, you compute its variance. Its variance will be something like, order epsilon times the cut value. Okay, but the intuition is really, because we cannot, if there's many edges inside this component, inside this set SC, large number of internal edges, they have to be supported on many nodes. There will be many samples to use. Okay. Okay. So just to do basically a warm up, basically this finishes the estimate. Are there other questions about the estimate or the correctness proof? Okay. So you finish this by doing a variance calculation. And you can get a high probability bound by repeating this and say at the end doing a median estimate, right? This is a sketch. We can do a lot of algorithmic stuff actually. So one note that I should mention, that in the construction we use sparse cuts. Okay, so it looks like preprocessing should be exponential time because we're solving a hard problem. The cool part here is that it is one of these kind of nice situations where doing approximation is actually okay because it will translate into the size. So if we do alpha approximation for sparse cuts, then this loss of alpha will just go in size. Okay, so if, for example, we will use the fastest sparse cut construction by Alexandr Mandry, at least that I know of, then in general we will obtain something like runtime, which is mn to power 1 plus delta, and the space will be n by epsilon times a polylog. This polylog power depends on delta.
Excuse me.
Yeah.
You're not actually computing sparse cuts. You're looking for a partition, a cut, so that the number of edges is less than or equal to 1 over epsilon times the number of nodes on one side.
Precisely.
You can do that in polynomial time.
If epsilon is constant.
What do you mean epsilon is not constant?
Well, so...
You're asking the question for an epsilon, right?
Right. I think of epsilon, okay, so this is one option to approach it. Sorry?
The computation of that is done in strongly polynomial time. It's independent of the value of epsilon.
Is it the case, or?
Yeah. I can show you later.
So why doesn't it solve the sparse cut problem then, or?
Because in the sparse cut you have a restriction. Well, I don't know exactly how you define sparse cut, but you have here you don't restrict which side will be less than or equal to half, right? One side is always going to be less than or equal to half.
I want the smaller side. The smaller side to have this.
Okay, so that's like expander. So
it's like expander, yeah.
Okay.
Yeah.
Okay. So that's how. Yeah.
Okay.
Yeah.
Okay. So let me show just. Okay. So this is a sketch. Now the question is, we relax some things. Is it still useful? Right? One of the ideas was to, okay, let's try to speed up things, right? And let me show you an application for this. Definitely would be interesting to see more applications, but just to give you one application, and it is more in the realm of space-limited algorithms, basically streaming sketching type algorithms. And the idea is to do sketching for global mean cut. So imagine the situation where you have a big graph. It is distributed over many agents, many computers, and each computer has to compute a sketch of each part of a graph, sent to a central node, and that central node needs to compute the global mean cut of a union of the graphs. So this is a theorem statement for a partition of 2. But in general, it says that we can compute a sketch of a graph G of size n by epsilon times per log, so that given sketches of 2 graphs G1 and G2, this is enough to compute the mean cut of the union of G1 and G2. Obviously extends to more than 2 partitions. And just to mention that basically a lot of very nice work on streaming algorithms for computing sparsifier cutter and spectral sparsifiers will get a 1 over epsilon squared dependence on epsilon as opposed to n by epsilon. Okay, so previous approaches to computing the global mean cut, just to make sure. Okay, so how do we do this? The idea is simple. Basically what we'll do, we'll store 2 cut sparsifiers. One is our relaxed one. And second is we will store a classic sparsifier, which is kind of a graph for all, but which works for, say, constant approximation, something like 1.5 approximation. Okay, and this will, since epsilon is a constant, this takes only n log n space. And now the idea is, why is this enough, right? So David Karger proved a nice theorem saying that there is only polynomial number of cuts which are within a factor of 1.5 of a global mean cut. Okay, so we can list all such cuts using this sparsifier. Okay, this list will include the actual global mean cut, and for each of the potential cuts in this list of n cubed cuts, we can verify it or estimate it up to 1 plus epsilon approximation using the relaxed sparsifier. The basic idea is that the sketch is good wherever you are doing a polynomial number of non-adaptive samples, queries. Okay, this is the idea. Okay, so let me switch gears. Let's go to the lower bound. Are there other upper bound questions about upper bounds?
Can you show again how you get these expanders? That is, you're checking whether there is an expander less than or equal to 1 over epsilon, right?
Okay.
How do you do that? I missed how you do it. It's an NP-half problem, as you pointed out. And how do you achieve that or the approximation?
So we will use an alpha approximation for this. How do we do this? There are much better experts than me in this audience, so I won't even try to attempt, there are, like log n approximation.
So alpha can be log n here?
Alpha can be log n here. Yes, so this alpha, which is log n, will go into the size.
Okay.
Just, just going through the proof, it should be simple to see that, if we just overestimate basically the number of edges is a little bit more by a factor of alpha, we just store more of these edges in this second part where we store the edges across sparse cuts.
More in the bounds there, this extra factor of alpha?
So what are the bounds? So,
You said there is the counting of 1 over epsilon per node.
Okay.
But it seems like it will have to be multiplied now by alpha.
Precisely. So this is why the size will increase by a factor of alpha.
And alpha is log n.
Let's say log n, yeah. Depends on, there is a trade-off between the runtime to compute this approximation and the approximation. So in particular, if you want near linear time, then we need to go to log to a bigger power.
So one issue that can happen if you use an approximate sparse cut is isn't it possible that you still need to do recursion on both sides?
Yes.
So, but if you get a really small sparse cut and the big side is big, how do you bound your recursion?
This is why it is MN.
Okay.
Yes, yes. It would be.
There's an MN. I
There
missed
is.
the MN. Okay. Thank you.
No, very good point. Yeah, I mean, it would be nice to make it an actual linear time algorithm. Yeah.
Right.
Or at least n to 1 plus delta.
Okay.
Okay, lower bound. So let me kind of show the principle of a lower bound at least. So, I mean, in general, of course, the question kind of, before kind of stating the actual theorem, the question that should be asked, okay, we had two relaxations. Are these relaxations necessary? Okay, what were the relaxations? One is that instead of a graph H, we're using a sketch H, so it's a data structure. This is one. Part two is that each cut S is preserved with high probability. Are both of these necessary? I don't know about this one. For this one, we prove a lower bound. And in particular, we say that, so it is not only a graph size lower bound, it is an actual information theoretic lower bound, saying that the amount of information that needs to be stored to be able to sketch every cut S, without any probability, right? I mean, with probability 1, this requires n divided by epsilon squared bits. Okay, I mean, this can also be used to prove that the actual graph size actually has to be n by epsilon squared as well for cut sparsifier, but this is what we focus. I mean, in some sense, this is it's a stronger theorem. Okay. And the proof goes really via communication complexity. Okay, and we really kind of thinking about it, what has to happen in this lower bound is that we really need to use the fact that H will be able to ask an exponential number of cut queries. Okay. All right. So let me do proof outline. Let me set up kind of how a lower bound proof looks like. So it is until 12, right?
Yeah.
Okay.
Go a minute or two beyond for me to finish the proof.
No, it's okay. I mean, at least to give an impression of this, right? It should be enough. So let me set up just some parameters so that it simplifies the problem a little bit. So let me set up epsilon to be something like 1 over root n. R is essentially 1 over epsilon, but it will appear somewhere a little bit later. So basically, what we want to prove is that note that n by epsilon squared now really looks like n squared. So we want to prove that for this setting of epsilon that we need n squared bits, omega n squared bits. Okay. So communication complexity, let me show up how this looks like. So this is our supercomputer Alice. Well, not our, but Leicester University computer Alice. And this is Bob. And it really kind of shows that the amount of information that or input that they get will actually be different. So let me. I'm setting up a communication problem. Okay. So let me describe what it is. So Alice, which has lots of storage, will have as input n strings. Each is a Hamming vector of length n. Okay. So there is a total of n squared bits. Bob has much less information. It has a string, which is a Hamming vector of length n, and an index between 1 and n, index k. So now, we need to solve a problem by communication. This is the problem that we need to solve. We need to distinguish whether the delta stands for Hamming distance, whether the Hamming distance between the string t that Bob has and sk. So basically, it uses this index k to index one of the strings that Alice has, and we need to check. We need to compute, in some sense, the Hamming distance between t and this indexed string sk, and we need to check whether the distance is essentially large or small, where basically these strings are close or far. Let me use this terminology. And close means that this is less than, so think about the strings as being random, right? So with some constant probability, it is less than n by half minus standard deviation versus n by half plus standard deviation. or order standard deviation. So this is Vizar, right? Vizar is roughly root n. Okay. So this is the problem we need to solve. How do we solve it? Basically, Alice sends a bunch of information to Bob, and the information cost is essentially how many bits need to be sent. Okay. So this is a communication problem. So what we'll do is that we will show how to solve this communication problem, assuming that we have a solution for the sketch problem, okay, for the cut sketch problem, and then a lower bound on this problem, which I guess I'm calling index of gap hamming. Then a lower bound for this problem, a communication complexity lower bound for this problem will imply a lower bound on the size of H. Okay, in particular, we'll show that Alice cannot do much more than send its entire information, basically n squared, order n squared information, and this will mean that H also has to have size which is roughly n squared. Okay, does this make sense? Okay. Okay, so what is, why it is called kind of index gap hamming? Well, it is essentially an n-fold of gap hamming problem. Gap hamming problem is really where Alice just has one string of length n, Bob has another string of length n, and you need to distinguish this, basically close or far, basically half distance minus standard deviation versus half distance half plus standard deviation, and this is a very nice problem, people study it a lot, and that particular problem requires size n. And it is, in some sense, an index of this gap hamming, where it says that we are not solving this problem, but Bob has an index k, and it has to solve the kth gap hamming problem. Okay, so in some sense, it's a combination of index and gap hamming. And it, okay, so there is one kind of, in some sense, technical issue that there is a particular distribution. And the distribution is such that, we need a lower bound for a particular distribution just because of, we are later doing a reduction. And in particular, the distribution is such that all these strings are random, conditioned on this delta satisfying one of the two conditions. Plus, it should say that all the strings have exactly weight n by 2. And then one has to prove that this requires n squared communication. Okay, this problem. I'm not gonna go into details how to prove such n squared communication lower bound, but think about this as combining two problems which are kind of very fundamental in communication complexity. One is indexing problem, which essentially requires full communication, gap hamming, which requires full communication. It shouldn't be surprising that their combination requires n squared communication. Okay, so now, what I will show is how to reduce this problem, basically. So assuming that this problem index gap hamming requires n squared size, what we want to do is that we want to show that if we can solve this cut sketch problem, that we can solve this problem as well. And the idea is really kind of to do some kind of embedding of one problem into the other. In particular, Alice and Bob will use this cut sketch construction to solve their problem, this index of gap hamming, and it works the following way. So we need to construct some graphs, of course, right? So Alice will construct a graph G, which will have 2n nodes. So, sorry for switching from n to 2n, but it just simplifies the description. And what it will do is it will compute the sketch. Assuming that there is a sketch algorithm for G, it will compute this cut sketch H, some data structure of G, and it send that information, basically that data structure, to Bob. Okay. And then Bob will use H to decide on this problem, on this communication problem. Okay, so pictorially, Alice, Bob, So Alice constructs a graph G of 2 nodes given its strings S1 up to Sn. How it is constructed, this is the picture. More or less should be kind of self-evident, but this is a situation for n equals 4. We have a bipartite graph, n nodes on left side, n nodes on the right side. On left-hand side, nodes will correspond to the string S, and this will correspond to the n coordinates, and basically the edges correspond to the bits that are set to 1. Okay, so in particular, the degree, say, of each node here will be exactly n by 2. Okay, now Bob, okay, so we construct the sketch H, send it to Bob. Now Bob, what it does, it has a string T of length n, it constructs a set T on the right-hand side. So for example, again, kind of using this binary representation kind of encoding. So if T is equal to 0, 0, 1, 1, this corresponds to the last two nodes, right, being in the set T. This is the definition of set T. And then what it does is the following. It computes a set S of size n by 2 that minimizes on the left-hand side, that minimizes the cut value of S union T. Right? So, here is one example of such of a set S. It consists of 1 and 3, and basically what it does, it finds this set of half the size on the left-hand side that minimizes its cut value, or put differently, it maximizes the number of edges that are inside. Okay, so intuitively, this chooses the strings that have smaller Hamming distance to my string T. Right, modulo all the approximations and stuff. What it intuitively does, it really chooses the strings that have smaller Hamming distance to set T. And basically, and indeed, kind of at the end, Bob outputs that we are close if this index k is inside the set S that has been chosen to minimize this. I see some puzzled faces.
One obvious question.
Right.
Why didn't Bob just take a look at? It knows K, right? So why doesn't Bob just look at SK and count the number of edges between SK and T?
I cannot count the number of edges because I have a sketch which just tells me the cut values.
Right. Okay, I see. And that is not a good estimate.
Right. Precisely.
Okay.
So yes, if I just take this and I take SK and I look at the cut value will be very large.
Right. So large that the standard deviation on it will swamp out your attempt to count the number of internal edges.
Precisely.
Okay.
Any other question? Okay. And I mean, in some think about this as it couldn't have worked, because for that question, if this is what Bob asks, then this relaxed cut sparsifier would have worked, actually, because it is just one non-adaptive query. It works with high probability. Okay, so basically, just to give an intuition of what it's mostly like repeating what I just said. Just writing a little bit in formulas. So basically, we will again switch to this view of counting the internal edges because it's just a little bit more convenient here. So the cut value of any union of two sets S on the left-hand side and T on the right-hand side is essentially, this is the sum of the degrees on the left-hand side plus the sum of the degrees on the right-hand side minus the number of internal edges. Number of internal edges can be viewed as iterating over all vertices on the left-hand side and counting the neighborhood, the intersection of the neighborhood of this of the string Si with the set T. So let me define a phi as being this. Basically, the number of edges between the set T and a particular node Si, right? I call this Fi. So what Bob does, it chooses S that maximizes this sum. Right? So again, kind of intuitively, if there is no approximation, right? If all this works with no approximation, then Bob will really choose all the i's that are essentially maximal Fi. And just because of our conditioning that, let's say if we consider a closed situation where this delta is less than n by half minus r, then this Fi is more than the average in some sense. So it should be in the first half of Fi's. Okay, so let me. This is what we need to prove. Let me just kind of explain this again. So think about this, just repeating what I said. So think about these Fi's, right? We choose a set S of size half of how many edges there are on the left-hand side, right? So this is basically means that we'll choose all the i's that are in the first 50 percentile of all these counts. Okay? And each of these Fi is distributed as binomial distribution. Okay? There is some error, right? And this is why it is not obvious, kind of. Namely that we compute this up to 1 plus epsilon approximation error, which in total gives us an additive of n to 1.5 value. So, so kind of pictorially we have, we have this line, these are these counts Fi, and we have a bunch of them here. And kind of somewhere here, which is n by 4, is the expectation, and they are kind of distributed kind of around this value. And what we want to say that if some I is close, basically in our sense this Fi is larger than the expectation, then it should be on this side, and it should be roughly in the first 50th percentile of Fi's. Of Fi. Okay, so let me tell this differently a little bit. So let me consider a set L of indices I. This is our indices on the left-hand side, such that Fi, the number of edges between I and my set T, is bigger than the expectation plus standard deviation. Okay, note that these are exactly i's such that if k is equal to I, then the answer should be close. Right? This is the number of edges which is kind of the negative of the distance. So this means that the distance is less than, it should be on average minus standard deviation. Okay, so else are things which are kind of average plus standard deviation. Okay? So if, just repeating the point I mentioned before, is that if there is no approximation, then k is in L even only if it is close. Right? Just because of all the concentration. But still, with approximation, it has to be the case that 80%, let's say, of L must be contained in the set S. So S, L in some sense the ideal set, S is what we get by approximation. So 80% of L must be contained in S with, say, 90% probability, because otherwise the approximation is too large. Right? Because otherwise a constant fraction of L, which is roughly linear in N, has to cross basically a standard. So this is n by 4 plus standard deviation. This is n by 4 minus standard deviation. So basically a constant fraction of things have to cross from here to here. And the distance here is standard deviation, which is roughly root n. So the total error, so if this doesn't hold, then the total error should be around n to 1.5. Which is not allowed because we have an additive error of at most n to 1.5. Okay, so that finishes the lower bound. So let me just conclude. Again, what this talk was about is about cut sparsifiers, which has size n by epsilon. In particular, linear dependence on 1 over epsilon, under two relaxations. One is that the sketch is not a graph but a general data structure, and 2 is that the guarantee is with high probability per query, per cut query. And also realization 2 is really necessary, otherwise we need n by epsilon squared size. So let me mention a few natural questions here. So first one is, does the first relaxation is necessary? I mean, maybe we can do this for each guarantee, basically, with high probability, just by using a graph. So using the normal estimate, not this kind of negative estimate. So just count the number of edges across cut as opposed to some degrees minus number of edges inside. Or maybe there is a lower bound. Question 2 is, what are other applications where this with high probability estimate is actually sufficient? In particular, this seems to definitely be usable in applications where we just ask a polynomial number of non-adaptive queries, or say logarithmic number of adaptive queries, I guess. Maybe I shouldn't say that. Part 3 is, can we prove the same guarantee for spectral sparsification? And David Woodruff with co-authors show that some improvement over 1 over epsilon squared is possible. So in particular, we obtain 1 over epsilon to 1.6. If this is correct. Okay, good. Thank you.